Hey Phys 1 kids, Campbell here. In our second video on rotational motion, we're going to talk about the center of mass and the center of gravity, which is where objects will rotate through or things will balance. So the center of mass is defined as a point at which all of the mass of an object is thought to be concentrated. So it's where it acts like it is all concentrated. We use this for extended objects. We say it's the average location of the mass. And in fact, you'll see when we go to calculate it, it is just a weighted average of the masses of an object. Now, if I have a uniform object, something where the mass is spread out and not concentrated in any one location, then that center of mass is at the center of my uniform object. Now, that means that it also may not be located on the object. Like if you think about a uniform donut here, or a uniform ring, the center of mass would actually be in the center of the object, which doesn't happen to be on the object at all. So that's totally cool. The center of mass may not be on the object. Now, that's almost the same as the center of gravity. Let's talk about the center of gravity, and we'll talk about when they're the same and when they're different. The center of gravity is the point where the force of gravity is acting. So if we hang an object from the center of gravity, it does not rotate because it's the average location of the weight. In fact, when we've been drawing our free body diagrams, we've just been drawing the force of gravity, just pointing straight down from an object. But if I had like an extended object, like say I had a uniform sphere, then when I draw my force of gravity vector, you're actually supposed to draw it from the point of the center of gravity of the object, which for uniform objects at its center. So we would draw the center of gravity the force of gravity for a uniform sphere from its center. So its free body diagram would actually look like that. So we wouldn't put it at the bottom and draw it down. We'd draw it from the center of gravity because that is the average location of the weight of the object. Now, what's the difference between center of gravity and center of mass? I mean, besides the fact that center of mass is the average location of mass and center of gravity is the average location of weight. Well, they're really not different, at least in terms of their location, as long as the acceleration due to gravity, g, right, that's the acceleration due to gravity symbol. As long as it's the same throughout the object, then the center of mass is the same as the center of gravity. It's the same location. But if you have like a super huge object, so big that the center of that acceleration due to gravity is different as you move through the object, then the center of gravity and the center of mass will be different, or their locations will be different. So center of mass is the average location of mass. Center of gravity is the average location of the weight or the force of gravity, which may be the same and usually is the same. We don't usually deal with objects that are so big that the acceleration due to gravity changes as we move through them. Now, one thing that's pretty cool about an object is that it'll balance if the center of gravity is above the area of support. So here I have a uniform meter stick, and if I put my finger in the very center of this meter stick, it will balance because my finger is below the center of gravity of this object. Uniform objects, remember, the center of gravity is in the very center of them. Same thing with a car. If our center of gravity here is above the center of support, which is with tires, right? You're completely balanced when you're there. The object is balanced. But if we start to tilt a little, now my center of gravity, you can see, is not over the center of support, and so I'm not stable. However, if we tilt that car enough, so the center of gravity now is located above the center of the support, so the base on either side is the same, it would actually balance if I could get it right at that perfect spot. Experimentally, finding the center of gravity is actually pretty simple. One, I could just stick it on my finger and find out where it balances. So in a uniform meter stick, it's the center, but what if I attach some sort of mass to the other end? So I just stuck a heavy mass, it's actually a magnet, to one end. Now it's going to balance let's see, where is it? There it is. Now notice my finger is closer to the mass, farther from the end, because I've shifted the center of mass or center of gravity of my object. So now my finger has to be close because this mass is here. If the mass wasn't here, it would just fall. You can do this for an irregularly shaped object by actually suspending it from a string from 1 or 2 points. And if you draw a straight line from when it's stopped moving, we draw a straight line down from that string. Okay, we'll just use the dotted line there. And then we switch the location of the string and we draw another straight line. The center of gravity is actually where those points intersect. So if we draw these vertical lines straight down from where it's hanging, and we do this a couple times, the center of gravity is going to be at the intersection of those points. Pretty cool, huh? Now, another interesting thing about, if you think about an object like this meter stick here, it's not really a meter stick, okay, this ruler, right? We said that the center of gravity of this was at the very center. It's a uniform, basically uniform ruler. So if I shift this to the side, right, the center of gravity always acts straight down. So now I'm going to actually have a torque produced, which, remember, torque causes rotation. So if I let go of this ruler, right, it's going to go back and forth and back and forth. And it'll keep doing that. It would actually, if there was no friction, it would do this forever. But unfortunately, there's friction. So eventually it's going to stop, and it'll stop when the center of gravity is directly below or above the pivot point. So now there's no more torque acting, right? Because the torque is straight down parallel to the radial line. All right, let's get to calculating. We've talked about how to experimentally find it, but now let's talk about how do you calculate the center of mass. The center of gravity, we just use mg instead of just mass, but they're going to be about the same thing for us. So the position of the center of mass is a weighted average. So what you're going to do is you're going to take the mass times a distance. And honestly, you just choose where you want to pick that distance. You could this as your 0 point, and we could call this x, because then this would be the mass of star 1 times 0 plus the mass of star 2 times x, all over m1 plus m2. That way, it's less math. But as long as you're measuring both of the masses from a consistent location, then you'll get your center of mass. Now, if we have an extended object that has both a width and a length to it, then we actually also have to do the center of mass in the y direction. So we do the y center of mass. So same equation, it'd just be the y center of mass is equal to m1 y1 plus m2 y2 plus however many m's y's you've got divided by the total mass. And so you then have an x location and location on your x-axis and a location on your y-axis, and you go to that point, and that's where your center of mass is located. Pretty interesting, huh? All right, let's try an example problem. I have a 2 kilogram ball. I'm going to assume this is the 2 kilogram, and this is my kilogram, and this is my 5 kilogram ball, and they're attached to a 1 meter long rod. And I want to know, what is the location of the center of mass? Well, you know what? I'm going to just see how I set the 0 by the 2 kilogram and the 1 meter? We're going to just keep it that way, because then I lose one of my little calculations. So we're going to say mass times distance, so that 2 times 0 plus the 5 times 1 divided by the total mass, which is the 5 plus 2. So that means I have 5/7. So where does that put me? Well, that puts me somewhere around here. If 5/7 is actually 0.714. So it's closer on my number line here, right? This would be about 0.7. It puts me closer to the 5 kilogram mass, which should make sense because it's going to balance closer to the heavier mass. Now, we could instead, call this 0 and that 1. Right, if we did that, then we would have our 2 times 1 plus 5 times 0 all over 7. And now we get 2/7. So what's 2 divided by 7? Well, that's 0.28586, so it's about 0.29. So 0.29 measured from here is, oh, what do you know? Same location, right? So it's totally up to you where you want to set your 0 point. I always set it where a mass is because then it gets out of my calculation, right? Then this guy goes away or this one goes away and it makes the math a little simpler. But totally up to you where you want to set your 0 point and measure from. You choose. All right. Well, we're going to do some more of this in class, and we're going to look at rotation about the center of mass because that's another pretty cool thing. So I'll see you in class.